for some reason, I started seeing and she goes sliding down the pole and I was like, turn around.
Okay, let's start. Okay, you guys, what are we going to learn today? I will tell you. We're going to learn about mechanical energy. I'm going to teach you what mechanical energy is, and it turns out just to be the sum of the kinetic plus potential energies. Then we're going to learn under what circumstances non-conservative work is equal to zero. That is, under what circumstances is the work done by the non-conservative forces equal to zero. And then we're going to learn the conservation of mechanical energy that says if the work done by the non-conservative forces equals zero, then your initial mechanical energy is the same as your final mechanical energy. That is, your mechanical energy remains unchanged. Well, let's go ahead and learn this. It will be fun. It will be good and good for you. First, mechanical energy, which in this class we abbreviate ME. And mechanical energy is the sum of the kinetic energy and potential energies. I put potential energies because we're going to learn about other potential energies like spring potential energy and electrical potential energy. And I should even put kinetic energies because later we're going to learn that there's not only 1/2 mv squared, which you think of as linear kinetic energy, but we're also going to learn about rotational kinetic energy as well. But when you add them all up, that's your total mechanical energy of the system. So hey, let me ask you a quick question. Example number 1. Find how much work a 2.0 kilogram object 3 meters above the ground going 6 meters per second can do. Please do this problem now. And if I'm asking how much work it can do, then I'm obviously asking how much energy it has. So please get me the total mechanical energy of this 2 kilogram object going 6 meters per second. That's 3 meters above the ground. That must have been the fire licking our school. The flames licked the school. Oh, by the way, if you don't remember the formulas, please be advised kinetic energy is 1/2 mv squared and gravitational potential energy is mgh. I'm hoping you have those in your head already, but if not, those are the formulas. What is that? 58.8 plus 36. How many people are getting 94.8 joules? Hey, yay. Any questions or problems on this? Okay, then let's go ahead and turn our attention to the conservation of mechanical energy situation. Okay? Here, this is the formula we learned yesterday. the work done by non-conservative forces equals the change in kinetic energy plus the change in potential energy. But what if the work done by non-conservative forces is equal to 0? What if we get that special situation? Well, then I get 0 equals the change in kinetic energy plus the change in potential energy. Or I can write this as the final kinetic energy minus the initial kinetic energy plus the final potential energy minus the initial potential energy. That's the change in the kinetic and potential energies respectively. And now I can get those initial values on the left side of the equation. So I get the initial kinetic energy plus the initial potential energy equals the final kinetic energy plus the final potential energy. But the initial kinetic plus the initial potential energies, those are just the total of the initial mechanical energy. And this guy is going to be the final mechanical energy. So I want you to see, if the work done by non-conservative forces is equal to 0, then my mechanical energy of the system remains unchanged. But here in physics land, when a quantity remains unchanged, we don't say the quantity remains unchanged, we say the quantity is conserved. And so this is the first conservation equation you guys have learned of today. This is called the conservation of mechanical energy. And it actually has its own special name. It's the conservation of mechanical energy. Conservation of mechanical energy. I'll just do it here. And the conservation of mechanical energy says something very simple. If the work done by non-conservative forces is 0, then the initial mechanical energy equals the final mechanical energy. If the work done by non-conservative forces is 0, then the initial mechanical energy equals the final mechanical energy. That's it, the conservation of mechanical energy. Do you need me to provide focus?
Oh, you're okay.
Okay, well so now the next question, of course, is under what circumstances is the work done by non-conservative forces equal to 0? When is the work done by non-conservative forces equal to 0? So we get this wonderful situation where mechanical energy is conserved. Well, there's 3 situations. Here they come. The first situation is if there is no non-conservative forces. There ain't no non-conservative forces. You guys okay with that? Okay? If there are no non-conservative forces, that is, you've got an object and neither tension nor friction nor normal force is acting on that object. No tension, no normal force, no friction force, kinetic friction force, then for sure the work done by non-conservative forces is going to be 0 because there ain't no non-conservative forces. Can you think of a scenario where something is happening, an object is moving, but there are no non-conservative forces acting on that object? Yes, Ravi?
When you're on ice.
Okay, when you're on ice. Alrighty. Yes?
Free fall?
Yeah, free fall. Good. Beautiful. The most common, yes? Okay, in outer space. Yeah, beautiful. All of those are situations where those forces aren't there. They're not even present. And if those forces aren't present, there's no non-conservative forces. Now, actually, your guy on ice is not an example of number 1. It ends up being an example of number 3, and we'll see why that is later. But by far the most common situation where there just are no non-conservative forces is free fall. That's the one we're going to be dealing with the most. Free fall. Here comes the second situation. What if I told you there were non-conservative forces present? could you still get no non-conservative work being done? What would have to be true about those non-conservative forces? Yes, Sean? Beautiful, equal and opposite. They'd have to cancel each other out. So you can have lots of non-conservative forces as long as they all cancel each other out. Then there'd be no non-conservative work being done because any work one force did would be canceled by any work one force did would be canceled by a negative work some other non-conservative force did. So yeah, if the non-conservative forces cancel each other out, that is their equal and opposite. The most common situation where this happens would be like a guy pushing a crate. Okay? Guy pushes crate at constant velocity. So he's pushing the crate at constant velocity. What forces are acting on that crate? Well, there's gravity and normal force, but how about him? The force he's exerting is to this direction, and it's a normal force as well, because he's pressing against the crate. What's opposing the normal force that he's exerting? Friction. Yeah, friction. And tell me, how do I know that in this case the normal force and friction are equal and opposite? What tells me that?
Constant velocity.
Yeah, constant velocity. If it's constant velocity, that means acceleration is zero, which means there's no net force. So you see, I got plenty of non-conservative forces, but they cancel. You see what I mean? So that's your second situation. You can have all the non-conservative forces you want as long as they all cancel. Then you can have no work being done by non-conservative forces. The third situation is one no one in this class would ever think of in a million years, so I have to teach it to you right now. Yo-yo. Imagine this yo-yo is going around in a circle. I guess you don't have to imagine it. I've got a yo-yo going around in a circle. Is there a non-conservative force acting on my green yo-yo?
Yeah.
What is it?
Tension.
Tension. Tell me, is tension doing work on this yo-yo? Is that yo-yo almost hitting my head? Hitting my hair? That was pretty cool. I'd hit to what is those Argentine bolos? Is that what they're called? The balls on the strings where they zoom and then like it trips up the animal and then they kill it. You know what? You ever hear those? One of those things. Oh. Yeah. I've got one. I've got a single bolo, whatever it's called. Bola? Are they bolas? Bolas. Bolas. Yeah. Okay, well anyway, tell me, I got tension, right? That's my non-conservative force. Is tension doing any work? Well, let's think about this. There's one clue that tension isn't doing any work. Do you remember this formula? The work done, the net work is equal to the change in kinetic energy. Okay? So I got tension, but what is it about this yo-yo? Maybe I'll go vertical. So what is it about this yo-yo right now that's telling me that the tension isn't doing any work? What's that, Fatima? Okay, there's no displacement. Just
Angel Vera, please report to the guidance office.
I thought they were going to tell us, okay, now you guys can So like, true, there's no displacement. It starts here and ends here. But I want to remind you, it's not displacement we're looking at, but kinetic energy. What do you notice about the kinetic energy of this yo-yo at all times? Yeah, it stays. It's not changing, right? There's no change in kinetic energy. This yo-yo is going around and around at a constant speed, right? And so because this yo-yo is going around and around at a constant speed, there's no change in kinetic energy. Dear
Attention
goodness.
all teachers, students, staff members. Just wanted to give you an update. We will go into second lunch as planned and scheduled today. We are continuing our communication with law enforcement and fire, and are currently safe on our campus. We will communicate with you if there are any changes. The fire is east of us.
If I have an asthma attack, do you think I can see at Awanda?
Thank you.
Awanda
We are not in any
Christian
danger,
boy.
Okay, you guys. So do you see that since there's no change in the kinetic energy of this yo-yo, I know that there's no work being done on this yo-yo? Now, if I were to hit Pooja in the head with the yo-yo really, really hard, it would probably be really bad for me, for my career. So I'm going to avoid hitting Pooja in the head. Okay? So now I want to remind you, tension is going that way, and my yo-yo is going that way. So why is tension not doing any work? There's lots of tension. There's lots of displacement, at least in the short term. You're right, eventually there's no displacement. But look at this moment in time. Tension, displacement. Why isn't my tension doing any work?
Because the displacement isn't in the direction of the... Is that right?
Yes.
Okay.
Good for you. Say that again.
I forgot now. The displacement isn't in the direction of the tension.
Yeah, in fact, what's the relationship between the tension and the displacement? What's that? Yeah, they're perpendicular. Do you remember that? Remember what I told you about the choo-choo train? Where the choo-choo train's going that way, but I push that way? Am I doing any work on the choo-choo train if it's going that way and I push that way? No, I don't get to take any credit for its progress because I'm exerting a force perpendicular to the direction of motion of the train. Well, this is no different. You see that? My tension is acting perpendicular to the displacement at all times. So although I've got plenty of non-conservative force, it's not doing any work because the non-conservative force is always perpendicular to the direction of the displacement. The yo-yo goes that way, the force goes perpendicular to it. You see? So that's the third scenario. The third scenario is that the non-conservative force is always perpendicular to the velocity. It's always perpendicular to the direction of motion, so it's not doing any work. You see, there's no force in the direction of motion. It's perpendicular. And tell me, what's the most common situation where this is going to occur?
A choo-choo train.
What's that? No. I mean, yeah, that's happened, but that more something more common than a choo-choo train and me pushing. I demonstrated to you, Logan. Yeah, ball and a string, or how about just any old circular motion? You know? Tell me, I've got clothes in a dryer. Normal force on the clothes. Is that normal force doing any work on the clothes? No, because normal force is always perpendicular to the direction of motion of the clothes. You see what I mean? So that's the last one. It's circular motion. Let me ask you, I've got a car driving around in a circle. Is friction doing any work on the car? No, because the friction is always perpendicular to the direction of motion of the car. See, whenever you've got a situation where your non-conservative force is perpendicular to the velocity, then it's not going to do any work. Okay, well, hey, let's do several problems. We're kind of going to hit, like, you know, 2 of those 3 pretty hard. Here we go.
Oh,
Sorry.
Okay. Here's example number 1. A 4-kilogram mass is at rest 5 meters above the ground. It falls to 2.0 meters. What is its speed at that moment? A 4-kilogram mass is 5 meters above the ground. It falls to 2 meters. What is its speed at that moment? If I can, I'll make a drawing. This is a 4 kilogram mass that's 5 meters above the ground. And then I'm going to drop it until it falls to be 2 meters above the ground. Well, first of all, is the non-conservative work equal to 0 in this situation?
Yes.
Sure, it sure is. Tell me, which of those 3 scenarios is this an example of?
Free fall.
Yeah, this is free fall. And in free fall, mechanical energy is always conserved because there ain't no non-conservative forces, right? So I can say, since the work done by non-conservative forces is equal to 0, I can use conservation of mechanical energy. You see? Now, if you're going to do conservation of mechanical energy, it has to be really clear in your mind what the initial and final situations are. This is the initial right here, when the mass is at rest 5 meters above the ground. This is the final situation right there, when the mass is 2 meters above the ground and it's in motion. So let's go for it. I got initial potential energy plus initial kinetic energy equals final potential energy plus final kinetic energy. My initial potential energy is 4 kilograms times 9.8 meters per second squared times 5 meters. My initial kinetic energy is 0. My final potential energy is 4 kilograms times 9.8 meters per second squared times 2 meters. And my final kinetic energy, hey, that's what I'm going to find. It's 1/2 times 4 times v squared. Are you okay with this scenario? You're just going to mindlessly plug in initial and final kinetic and potential energies. Whoops. That should be an F right there. And so now I'm going to do the punchy. Okay. The square root of it. I'm getting 7.7. Are you guys getting that?
Yeah.
All right. Then I feel very good about myself. Are you ready to do the problem on your own?
Of course.
Okay, then here's the problem you get to do. Here comes example number 2. A 2 kilogram mass, 8 meters above the ground, going 11 meters per second. Okay, so I've got a mass that's 8 meters above the ground and it's going 11 meters per second. What is its speed when it hits the ground? This is another free fall situation, so you get to use conservation of mechanical energy. Please go do this now, and I will walk around and help you. Wait, clear. Okay. Yeah, I see a correct answer in your feature. Good, easy. Alright, just put a zipper along there. See what we've got here. Sure. And you know that velocity is 11. Yeah, its initial velocity is 11. Final velocity, that's what you're trying to find, the initial velocity. Everything you have is correct. You do your math right and you got a win. Oh, your initial potential energy, that shouldn't be a 0. How high is it initially? Yeah. Now the final potential energy is 0. So far so good. Oh, we're so smart. That's a good thing. Being smart is a good thing. I mean, it'll get you hated like Hillary Clinton. Okay. Oh yeah, you're good so far. Yay.
If it hits the dot, is it 0?
Yeah, good for you. You're gonna get a right answer, I would assume.
When you know it's kind of
Good for you, Robbie. That's correct.
Okay. Because I'm thinking like it's on the
Brandon.
ground.
On the left side, you've got a that 11 should actually be 1/2 times 11 squared. You know, 1/2 times 2 times 11 squared. It's got to be the full-on kinetic energy. Don't just put 11 there. All right, Imani, you got a winner.
Gracias.
I don't know. Let me see what you got. Oh, I'm so sorry. You got it. Hey, your math is like not 8. What happened? I think
You got 16.7?
I think it's the same one.
You got 12.7, so that's the...
16.7.
okay, then its initial height is 8. And its
You
initial
said 60
velocity.
at first, that's why I was like,
Oh, oops.
Well, finally, potential energy is 0. See what you got here. Yay, okay. Did you get the answer? Yay. Yeah. On the right side, this is the initial gravitational potential energy, but there is initial kinetic energy. It's 1/2 times the mass times 11 squared. Good for you. Yeah.
I don't really get it.
Not like in the
good luck with that. You know what? Good luck.
1/2.
Sorry, when she does.
11 squared.
I lied.
And then so, and then 11.
Yeah, I know she did all that. Like I saw her counting it out, and I'm like, she didn't do the first 15.
You're not, oh, really? Because you're looking at me and I assumed you like wanting to interact.
Because for the quiz, Sean came out and
You're right.
I was like, alright, for sure, I get it. And she's like, she gave me different questions.
Sorry, what speed is it?
You have different questions.
No, for the quiz.
Okay, my head knows.
Because I don't
I don't know.
That was the quiz on the first the letters and the
Oh, we already got it.
Yeah, that was last week. That's what
Oh, I was talking about this.
No, last week.
Oh, yeah. Yeah, first grade and second grade.
I'm sorry, I was like, what's your question? Yeah, like who is Robert Walton and like describe him or
We got
something?
yeah, we're in the same group.
And it's like I shoot a little bit. And so I just like put a big emphasis on him being lonely and like
Yeah.
and then I read it and I was like, I know.
But I wanted to.
It's physics is right.
All the teachers that just don't know. We don't know anybody in class. They just have huh?
I don't know, you've seen the thingies, dude.
I told you to please second.
He said that's okay.
I always run out of time in this class.
Not 7 problems.
I blame it on the announcements.
Yeah, me too.
I emailed her. But I haven't like talked to you face to face, which is kind of my
Okay. Hey guys, we're gonna
I
have to
just
go
don't
through
know.
this together. I have to actually do 3 more problems with you in the last like 9 minutes of class. So I'm gonna have to go a little bit quick. But are you okay that initially, not only do you have gravitational potential energy, but you also have kinetic energy initially? And they both have to show up on the left side of the equation. On the right side, you just got 1/2 mv squared, so you end up with v equaling 16.7 meters per second. Any question or problem on this? Okay, then I need to give you a few more problems. Here comes the next one. Okay. I've got an inclined plane, and I have a 5 kilogram mass on this inclined plane. And that 5 kilogram mass is 3 meters above the bottom. And the coefficient of kinetic friction on this inclined plane is 0, so it's a frictionless plane. And I want us to get the speed at the bottom. Before we do this, there's something I want to talk about with this problem that I forgot to mention. You'll notice you got a speed 16.7 meters per second. Do you know what direction that's in? Well, here's the thing, you don't, right? Because if this 11 meters per second was straight up or straight down, then yeah, this final speed would be down. But what if this 11 meters per second was horizontal? Then that velocity would be at some weird angle, but the resultant velocity, when you did Pythagorean theorem, you'd get 16.7. So let's say there's someone below you and you want to hit them with a water balloon. Does it matter if you throw the water balloon up, down, or sideways? Is that water balloon going to hit them any faster whether you throw it one way or the other? No, because your water balloon has the same amount of energy whether you throw it up, down, or sideways. And so that water balloon is going to hit them at the same speed. Now, if you want it to hit them straight on the top of the head, then you better throw it straight up or throw it straight down. But if you don't mind it hitting them in the back, then you can throw it sideways, but it's still going to hit them at 16.7 meters per second. You see what I mean? That water balloon is going to have the same amount of energy no matter what direction you throw it. But let's turn our attention to this problem. I want the speed at the bottom. Tell me, are there any non-conservative forces acting on this 5 kilogram mass? Yeah, there's no friction, because friction is 0. There's no tension, there's no string tied to the mass. Is there normal force?
Oh, yeah.
Sure, plenty of normal force, lots of normal force. But tell me, why does that normal force do no work on that mass?
Because of number 3.
What's that?
Because of number 3.
Because of number 3, right. Do you see that normal force is always perpendicular to the motion of the mass? The normal force is acting that way, the velocity is that way, the normal force is always perpendicular to the velocity of the mass. So although there is normal force, it's not doing any work. And so, Ravi, do you remember earlier when you said an example of no non-conservative work being done was a guy skidding on wet ice, let's say? That's a correct answer, but not because there's no non-conservative forces, it's because the normal force is always perpendicular to your direction of motion. But you were right, you were fine, I just want to let you know it's that type. Well, tell me, since there's no non-conservative work being done, right, I get to use conservation of mechanical energy. He starts at rest. So let's go ahead and get his speed. Initially, all he's got is gravitational potential energy. At the end, all he's got is, kinetic energy. by the way, I made this mass 5 kilograms. Would I get a different answer if this mass were 2 kilograms or 10 kilograms? Why not? Why wouldn't I get the same? Why would I get the same answer? Yeah, I want you to notice that that's going to happen quite often with these conservation of energy situations. The masses cancel. It doesn't matter how big or small that thing is. If you took me and Anna East and put us both on the Luxor Hotel and Hotel and Casino in Las Vegas and had us slide down the Luxor, guess what? It'd be a tie, right? No one would win because it doesn't matter who's bigger or smaller. See, so it'd be a lot of fun and we So what's the speed of that guy at the bottom? What do you guys get? Anyone getting that? Yeah, 7.7 because it's the same scenario as that one there. 7.7 meters per second. Okay, here's the last problems I need to show you. Okay. Here we go. Oh my goodness.
Good afternoon, Eagle. Sorry again for the interruption, but we just want to keep you updated. The status remains the same. We are not evacuating. However, a local news station did report that, but please know we are not evacuating, and at this time, fire and police do not indicate any danger to us. Okay? Have a great rest of the day.
Okay. These constant announcements, they really make me feel a lot better, I'm like really confident now that we'll be okay. So we've got here a wrecking ball. And of course, when I say wrecking ball nowadays, what's the first thing you think of? Yeah, naked Miley Cyrus on it. So we got naked Miley on a wrecking ball, and it comes down here 12 meters. Okay, I'm not even going to tell you what the wrecking ball's mass is. I want you to get the speed at the bottom. Well, tell me, is this a conservation of mechanical energy situation? Why do you say yes? There's plenty of non-conservative force. Tension this is a wrecking ball. Tension is exerting a stupendous amount of force. Yes, Logan? Oh, that's right. That tension is always perpendicular to the direction of motion of the wrecking ball. So although there's tons, literally tons of tension, it's not doing any work. So I still work done by non-conservative forces equals 0. So I get to say that the initial mechanical energy equals the final mechanical energy, right? Tell me, how high up is this wrecking ball? 12 meters, so I got mg times 12 meters equals 1/2 m v squared. So I got v equaling whatever that is. Now, I wish we had more time. Times 12 times 2, square root of that. So I'm getting like 15.3. Okay. Man, I wish the bell was going to ring, because there's another scenario I got to prepare you for. What if that wrecking ball wasn't at a 90-degree angle? What if that wrecking ball was at, let's say, a 40-degree angle? Okay. This is 12. The bell's going to ring soon, so let me just show you this really quick. Let's say that's a 40-degree angle. Your key is to get the y component. That's 12 meters. So this from here to here is going to be 12 times the cosine of 40 degrees, which is 9.2 meters. So here's the last question I'm going to ask you. If from there to there is 9.2 meters, and we know that this is a 12-meter wrecking ball, what is the height of this ball above the ground? If you're thinking 2.8, you win. So be prepared to do some trigonometry. Good luck, you guys. Bye-bye.